Thank you very much for the introduction. Yeah, so this talk is about, as you said, the Portals framework. It's a framework for stateful serverless, and it's written in Scala 3. That's why we're here. And yes, that's all I wanted to say at this point. Okay, so serverless, probably you've heard the term much at this point. But what is serverless? Well, it greatly simplifies the way we can build and deploy applications, distributed applications on the cloud. The serverless programming model essentially consists of stateless functions and triggers. So for a application developer to write a serverless application, they write their function and they submit it to some framework, and this framework runs in the cloud and automatically executes everything and takes care of re-executing if the function fails, for example. Okay? So this has, as I said, greatly simplified things, but there are some challenges with traditional function as a service frameworks like AWS Lambda. The first challenge is that these don't have state. Okay? So in order to have state, you need to manually use some external state backend, some database somewhere. And also, functions cannot call other functions directly. So again, you need to manually call the trigger via a network request. And what does this lead to? Well, because of these two things, the consistency now is all the responsibility of the application, right? So the application has to manage the consistency. Because of these challenges, more recently we've seen stateful serverless frameworks. And in contrast, these now manage the state and also manage the function-to-function communication. So, and the challenge now is for the framework to ensure that these things are consistent, right? So the application no longer is responsible for ensuring that the state and the function-to-function communication is consistent. Rather, it's the framework's responsibility. Okay? And these are just some general desirable properties of such a framework. First of all, it should have these strong execution guarantees. This is what I mean by consistent. And we have a slide, the next slide is about this. It should also have good performance, of course, meaning high throughput and low latency, so we can use it for processing data, large amounts of data, and still at real time. And it should also be expressive enough so we can express the applications that we want to deploy in them. Right. For execution guarantees in message processing systems, we typically, we have three flavors of message processing guarantees. And the strongest one is exactly once processing. What I have here is a program. It's a program of two computing nodes or two functions, you can think of them. And here A sends a message X to B, and B, when it receives this X, it updates its local state. So in exactly once processing, the framework ensures that the message is delivered, processed, and all the side effects happen exactly once. Okay? So when we write a program like this, in a stateful serverless framework, this program will execute like this. We can expect that this state update will happen exactly once. At least once, in contrast, is when a message is processed at least once, then delivered at least once, so it could be delivered multiple times. And now, in order to preserve the semantics of this, the first application, so the first application which is on the left, if we want to preserve the semantics, we need to deduplicate any messages, and we still also need to have a transactional block because things might be processed twice. Okay, so here we need to add some failure handling code in this case in the application logic, which is something that we maybe perhaps would like to avoid. And at least once processing is the kind of guarantee you typically get in serverless functions and similar. At most once processing is the third flavor, and here messages are delivered at most once, so they might be delivered once or not at all, and they might be processed once or not at all, or they might crash in the middle of the processing, and then only half of the things happened and the bottom half didn't happen, right? So again, in order to ensure that we have the same semantics as the exactly once program, we need to have some more failure handling code. And in this case, we have this process A sending repeatedly the message X to B because it might get lost until it receives back some acknowledgement. And on B side, again, we need to deduplicate and do this in a transactional scope. And this is the kind of guarantee you might get in an actor framework like Akka, for example. So what's the point of the previous slide? Well, the point I want to get across is that programs in exactly once processing are contain solely the application logic. They don't have this failure handling logic when it comes to managing redeliveries or messages that are not delivered. Whereas these other execution models require extensive failure handling logic. And because of this, in the other execution models, you will likely introduce bugs because you'll have to focus a lot more on things that are not application logic and things that don't really matter much to the business value. So the greater conclusion is that the end-to-end exactly once processing makes programs significantly easier to reason about and significantly easier to write. And that's why in stateful serverless, most of the frameworks have adopted this execution guarantee to simplify for the programmers to write their programs without having to worry about these quite low-level issues. Okay, continuing from this first part, we're going to look at two programming models for distributed programming. These are stateful streaming and actors. And we're going to look at them just to understand a bit their properties and then continue from there. Stateful streaming is a very popular programming model. You might be familiar with Apache Flink or Google Dataflow. These are used for processing large amounts of data and doing so in a fault-tolerant manner. What you can see here is a program written in a streaming API. It's written in Flink API. It's the traditional word count program. We have a stream of inputs. Yes, you can see my mouse. And a stream is an infinite sequence of events. And in this case, we have an infinite sequence of sentences. So how can we process this? Well, we take this stream, we flat map it, so we split all the sentences into words. Then we create a word, one tuple here, where the one is the count of the word. And then we have a key by operation. The key by effectively partitions the stream into buckets where each word gets its own bucket. And we have a final sum aggregation here at the bottom, which aggregates on the second index on the tuple. So we aggregate up the sums incrementally. This corresponds to a logical representation, as you can see in the middle. And a logical representation here is just an acyclic graph of stateful tasks. This is how you can represent a program in stream processing. And the framework, for example, Flink, will take this and produce a physical representation, which has a few very important details. So first, streams here are represented as a set of distributed streams. These correspond to the physical network connections that transport the data. And also we might have tasks that are, tasks might be optimized and merged together. So we might do some optimizations, and also tasks are executed in a data parallel fashion, like you see here. So we might have a single logical definition of a task that's executed parallelly on the data. So this is what we mean by data parallelism. So we can use this to process large amounts of data, and consequently has been very successful. The actor model, on the other hand, is very much is very different. Okay, the actor model is incredibly dynamic, and this is just a quick overview of the actor model. An actor can do three things. An actor can send messages to other actors. Important to note is that an actor can actually send a message with a reference to itself to another actor. And in this way, the other actor can then send messages back to the actor, or can also forward the reference to another actor. And so we can have a very dynamic topology where actors form new connections to each other. So it's a very, very dynamic programming model. An actor can also create new actors, and an actor can also modify local state. So if we compare these two on 3 dimensions, performance, expressiveness, and correctness. First, on the level of performance, as I said, stateful streaming is widely used to process large amounts of data. It has high throughput and low latency and is suitable for real time. For example, Uber has several thousand Flink jobs running. This was in about 2-3 years ago. And ByteDance/TikTok, they have 40,000 Flink jobs running right now. This was the latest data from this year. So it's definitely used in practice to do these things. Actor systems, on the other hand, they don't have a data parallelism as such, but they have a task parallelism. But they're still very useful for these real-time applications that need good performance. Streaming systems are very limited and they're limited to only expressing static, acyclic graphs of tasks. And so we need to think about this limitation for a bit. So there's, first of all, it's not possible to interact with a streaming system by means of sending it a message and then receiving back a reply. Okay? So the only way a streaming system works is that it has an input stream and produces an output stream. So we cannot express a request reply with streaming systems. The second issue, as I said, is that it's not very dynamic, and we cannot express cycles in these systems. And cycles are necessary for many iterative programming models and so on. So these are very great limitations. Actor systems, on the other hand, are very expressive. You can express general concurrent computations. But expressing general concurrent computations also comes with many of the bad things about being so general, right? You might have deadlocks, you might have live locks, and there's many issues with that too. Finally, for the processing guarantees, as I said, in streaming systems, we have exactly once processing guarantees. And what this gives you is the illusion of a failure-free execution. So you can submit your application and stop worrying about failures. Whereas in actor systems, you don't get these kinds of guarantees. In fact, it's a very low-level programming model and oftentimes used to implement these high-level programming models like streaming systems. So it has a quite different target. And from this point of view of streaming and actors, we have asked that, can we combine some of the great ideas from both? And this is what we've tried to do in the Portals framework. We've tried to take the nice properties of streaming, the good guarantees, and the good data parallel processing capabilities. However, adding some of the nice flexibility of actors. And I will now show an overview of the programming model in Portals. And we have 3 main abstractions. The first ones are the workflows. These are stream processing pipelines. The second one is the atomic stream. And this is a transactional stream, which we use to compose workflows together. And we also have portals, which is the namesake of the framework. And these portals are used to get an actor-like communication. And more details in the next few slides. Of course, underneath everything, we still have end-to-end exactly mass processing. Workflows workflows consume and produce atomic streams. So here you can see a graphical workflow, and it has an input type T and an output type U of the events it processes. And internally, it's an acyclic graph of stateful tasks. It's very much a streaming pipeline. Then we have the atomic streams. Atomic streams are transport atoms. What is an atom? I'm highlighting one here. That's the other one? Okay. Let's hope it stays on today. All right. Here you can see an atom, and an atom is a batch of events. It's a batch of distributed events. So the lines which you see here signify these physical streams. And another interesting property is the atoms are totally ordered on a stream. And we can use atomic streams either to connect workflows, because a workflow produces and consumes atomic streams. And we also have a few operators on atomic streams, like generators, sequencers, which take two streams and create one sequence, and then splitters to split things again. Why do we have atomic streams? Well, it's to have this exactly once processing. And what does this mean? Well, to be a processor in our Portals framework, you need to adhere to the atomic processing contract. This means that you need to process the atoms atomically. And if you look at the description, this corresponds very much to my initial description of exactly once. So a processor needs to transactionally both consume the events, process the events, and then publish all of the side effects. And this has to be one single transactional step. It's very important. And if every processor in the system adheres to this contract, then you will have end-to-end exactly once guarantees. Now, of course, this might seem like a very heavyweight contract to fulfill, but there are in fact some. You can do it in quite optimized ways, right? You can do things asynchronously. It doesn't have to be in a batched fashion. And to give more of an intuition of how this actually works, here I'm showing how we can enforce the atomic processing contract on a workflow. And at the top, I'm showing here the Portals runtime, which is, if you know a distributed two-phase commit, this is the coordinator. And in a distributed two-phase commit, a coordinator would need to be highly available and reliable. So you would back it with some replicated state machine. And the coordinator will then issue a pre-commit, which then forces all of the tasks within the workflow here to start pre-committing once they have finished processing the atom. And pre-committing here means to both pre-commit all the state changes to the external file system and also pre-commit the newly formed atom to the output atomic stream. Once all the tasks are done, so the tasks respond with an acknowledgement here in 1C. And once all the tasks are done, the coordinator will have received all of the acknowledgements. And at the very moment the coordinator has received the acknowledgements, this is when the atom is committed, because the coordinator will then internally set a flag that it's now committed. And at that point, nothing can change anymore. And this is really what enforces the transactional mechanism. What happens next is the second phase of the protocol, where the coordinator will just issue all the tasks to finalize the commit. Okay. And again, so this might seem like it's a batched style processing, but in fact, Apache Flink and many other streaming systems have a way of doing this in a pipelined asynchronous fashion. So you don't need to wait for the commit to finish to start processing the next atom. And we have some links at the bottom, which you can read more about this. And finally, there's the new concept which we're presenting, which is really enabling the actor-like communication. and it's called portals. But it comes with a few restrictions, because we cannot have general actor communication, then we would not be able to do the things we want to do. So the restrictions are that the connections are statically defined, but dynamically reconfigurable. Okay, so the program needs to say which tasks or which actors are connected to other actors, and these connections are unidirectional because we don't want to pollute the connection space. And the second thing is that we don't allow to dynamically create any workflows or tasks. That's the second big distinction to actors. And with these first two, we have a nice property that our topology is static. And because it's static, we'll be able to use many of the techniques from well-known techniques from these streaming systems in order to enforce exactly once processing. A small detail is that the messages can be replied to, which is not always common. I know Akka Classic, I think, used to have a reply as an operator, and the Akka type removed it. So sometimes you have it in actor framework, sometimes not. The reason we have it is so that a replier does not have to have a connection to the requester. Instead, the replying task can simply reply back with the reply operator. And this way, we, again, limit the amount of connections we need, which is good for the efficiency of the protocols. A task with a portal looks like the following. Here I'm showing a portal task, and it's a task and an actor hybrid. It has the types TU, MR. TU stand for the input and output times of the types of the stream, and we have the types MR, which are the incoming message and the reply type. Then we also have this blue circle in this figure, which is a portal. And a portal, you can think of it as a named mailbox, very much like an actor mailbox. And we have the following rules. So tasks statically connect to portals, either as a sender or as a receiver. And every portal has exactly one receiving task. I can note also that a task could connect to a portal both as a sender and a receiver. This way, you could do some nice self-recursive patterns and so on. There's a few fun things you can do like that. Here. All right, to give some more intuition on portals and how we can use them, here we have again the word count example from the start, but now with a portal. And in fact, so the sum task connects to the portal as a receiver, and it will then reply to any requests which are words, reply with the count of the word. And then we'll have another workflow here at the bottom, which connects to the portal as a requester and sends it a request. And I hope you can see in the back of the room this. So this is what it looks like at the responding task. First, we need to create a portal, which we do here. We define the portal. We give it the message type and the reply type, as well as a name. And then somewhere within the workflow definition of this word count application, we have a task with a replier that connects to the portal. And we have these three dots here, which hide the original word count sum task definition. And we have a handler here for the requests, these actor-like requests that come in, the messages. And within this message body, what do we do? Well, first we access the per key state, which is some typed state for this very task. And it's per key, meaning that it's partitioned by key. Events have some key attached to them, and these events will arrive at the corresponding partition. And we give it a name count, and we give it a default value 0. And then we create the word count reply that we want to reply, which is this tuple here. So we get the value from the state, and we simply call reply on the word count. All right. On the requesting side, we have the requester now getting a reference to this portal through the registry. So this is some entity which allows us to get these remote references from other applications. And again, we give it some type and a longer identifier. And within the workflow definition of this requester, we create a task with a requester connected to this portal and provide this event handler. And what happens here, we build the event, the request from some word. Here I'm just not showing how the word is built. It's not too important. And we can then ask this reference, the request, which essentially this is essentially means that we send a request to this portal and we get a future back. And the future is a future of the replied value. So what we can do then is we can call onComplete on the future, which and provide here our block of code, which will execute once the future has completed. Okay, so once the future has completed, which means that the reply has come back to this task, then this code is executed and we can do things. We can, for example, now emit this word count on our outgoing stream. But we could also issue more requests recursively within these continuations. The way we implement continuations is a very critical part of what we do. So what happens when we invoke this onComplete method? So first, the continuation is stored together with metadata to the task's persistent storage. And so this way it's persistent. And we also use the Spores3 library to ensure that this is safe to do. When the reply arrives back, well, we load the continuation from this persistent storage and restore all of the context from the metadata, and we can execute it. And another important thing is that the execution is serialized with other events, so we don't have any strange data races, and things are still easy to reason about. And then this mechanism simply ensures that the continuation is persistent and not ephemeral. So if an actual physical processing node crashes, the continuation will survive because the continuation is in persistent state, which is replicated somewhere on an external file system, and we restart the task somewhere on a new node and load the state, and then we can load the continuation. Okay, so this is very, very nice. Yeah, just before some examples, I'll give you just a few more, just a slide here on implementation details. We have, so in order to implement the exactly once processing, we use similar mechanisms to Flink and Kafka. And for the portals, as I hinted earlier, we leverage the fact that the topology is static, so we can still do things. The performance, we really leverage the data parallel processing capabilities of the stream processing model. And everything that we have is built on streams. We have two types of streams, atomic streams, which I've shown you. But we also have reply streams, which is like an internal thing. And the reply streams are used to implement the portals. There are atomic streams you can reply to. And another distinction is that they're multi-producer, single consumer. So whereas the atomic streams are single producer or multi-consumer. Okay, so we have two examples to look at. The first example is the shopping cart example. It's the canonical stateful serverless example. And we'll look at how to compose workflows, how to do microservices style things, and how to use futures. And the second example, we have actually implemented the actor model on top of the portals framework as a library, and that uses the fact that we can have cyclic workflows. The canonical shopping cart example consists of two services. We have a cart service, which consumes client requests to either add to cart, remove from cart, or to check out an order. And we have an inventory service, which manages items in an inventory, so every item has a certain count in the inventory. And in our example, the cart will consume these requests. It will then, for example, for the add to cart event, it will have to check with the inventory if it can actually take this item out of the inventory and put it into the cart. But we can also continue this example beyond what's traditional. We also have an order service which consumes the checked out carts and produces the final orders. And then we have an analytics service which takes all of the orders and processes them and produces a nice top 100 list of most purchased items. And the idea is further down the line, perhaps you could start even more services that then use the analytics service to, for example, do recommendations and so on. This example is on our repo. You can check it out. And let's see if I can run. So yeah, you can run it. I'm just going to run it, and then I'll show the code in the slides, some highlights. Yeah, so you can run the example, and this is now throttled to 4 events per second, so we don't get overloaded. And we can see how at the start the inventory needs to be populated, so we just start ingesting new items into the inventory, and over time we'll start seeing actual orders being produced and also this top 100 list of purchases. So we can come back to it in a moment to take a look. Yes. Oh, crap. Right. So this is now how you can write an actual Portals app. So it's perhaps a bit verbose. I hope you can see it in the back. So first you create this Portals application. You give it a name, and then within this block here we can define our application. First, here we define the inventory operations generator, which is a generated stream of initial inventory operations to populate the inventory with items. This is defined somewhere else. And then we create a portal. Here we give it the name portal. We have the message type and the reply type. We give the name, and we also provide here explicitly a method to compute the key from any event so that the portal requests are sent to the corresponding partitions by this function that we have here. And here we now create the workflow. So we create it by saying workflow. So we have the incoming or the input event type to the workflow and the output type of the events. And I'll forward. And then what happens? Well, we consume this inventory operators generator stream. Perfect. And we do the key by operation, followed by having a task, which is shown in the next slide. And then we give it a name inventory, and freezing the workflow finishes the workflow, so it cannot be modified anymore, and returns a reference so we can later on use it for further down in our code. And this is what an inventory task looks like here. So this is a task factory, and we use the task with replier factory. We connect it to the portal, and we have two message handlers here: the onNext, which are the regular stream events, and onMessage, which is for these actor-like messages that we need to process. And then we create this state, again, a per key state. So typed state which exists only in this keyed context for a specific partition. We give it a name and an initial value. And so what does it look like when we want to handle a GET request? Well, we can write this method here, and we can simply, when we get the request, we can look into the state here and see if we have at least one item in the state. Then we can reply with true and decrement the state. Otherwise, we reply with false and say, like, there's no item you can take from the inventory. And the cart workflow is or application is very similar, and we'll skip to the cart instead, like this. And you already seen the bottom method similarly in the word count example, how we can use futures to send a request and then call the onComplete method. All right, because I'm running a bit short on time, I'm not going to show the code for the actor model, but you can come talk to me just after and we can take a look. But we have time to talk about this. So implementing the classic actor model is actually super simple if you have a cyclic workflow. The idea here is that the actor messages are routed back on the actor message stream and cycled back and then partitioned so that the actor messages arrive to the correct actor. And we execute a virtual actor runtime on each task, which essentially loads the actor from the state, executes it, and then saves the actor back to the state. And this is really how it's implemented. And I could. Okay, so we have this cart application running. You can see we have some orders happening. And let me tab out. You can also run this in our repository. We can run the Fibonacci example on here. So this is very fun, right? Didn't say. Sometimes it takes a moment to update. All right. We have a Fibonacci number of 22. Yes, this is also on our repository. Besides this, we actually have a playground, and we use the fact that you can compile Scala to JavaScript with Scala.js. So you can run portals applications in the browser. And our goal is also to use this to run the portals applications on edge devices in the future. But right now, it's more just for playing around and to communicate a programming model. Here we have a recursive example, and you can edit the code on the left side and then run it, and you see like the output on the right. So this is pretty. It's a good way to teach others about your programming model and so on. And I would definitely check out Scala.js if you haven't done so far. We have links on the last slide also to the repo and the playground. So this is the almost last slide, just again to reiterate some of the main points. I'll present the portals now, a stateful serverless framework that combines both the guarantees and performance of stream processing frameworks and systems with some of the flexibility of actors. It's all written in Scala 3. Right now we're working a lot on the distributed runtime, and we're planning a release this or next year. We have a link here to the repository, and we also have an academic paper if you're into that stuff. And thank you also. Thanks to many of the other contributors, Philip Haller and Paris Carbone, as well as many students who are listed here. So we have a tutorial. You can see the link there to read more about it. We also have the repository and the playground. Thank you. That's all.